Before beginning to use your new quick align system, it is important to have a clear understanding of the theory behind wheel alignment geometry. Understanding wheel alignment geometry will streamline the process of correcting characteristics that are outside the specification limits. The geometry characteristics considered in this discussion include lateral offset, thrust, toe, caster and camber. The ideal wheel orientation for all wheel positions in the vehicle is perpendicular to the ground and parallel with the centerline of the vehicle. This orientation produces the lowest rate of tire wear since each tire rolls in the same direction the vehicle is traveling. In reality, there are always discrepancies between the ideal geometry and the actual geometry, which can reduce the performance of the vehicle. Even subtle alignment discrepancies can dramatically reduce fuel economy, handling, and tire life. It is for this reason that the ATA Technology and Maintenance Council has specified tolerances for alignment geometry in their recommended practices RP 642 guideline for total vehicle alignment. The most important portion of RP 642 is the specification of drive axle alignment. When one or more of the drive axles are misaligned, the drive wheels apply a continuous lateral force to the entire vehicle. This lateral force requires the driver to continuously compensate with the steering wheel. Consequently, misaligned drive axles are the #1 contributor to steer tire wear, and steer tire life can often be doubled by maintaining proper drive axle alignment. To correct drive axle misalignment, there are two characteristics that need to be considered. The first characteristic is the lateral offset of the axle. The lateral offset is the side-to-side bias of the axle in relationship to the center line of the frame. The lateral offset is positive when the axle position is offset toward the passenger side, and negative when the axle position is offset toward the driver's side. The second characteristic is the thrust angle of the axle. The thrust angle is the angular bias of the axle in relationship to the center line of the frame. The thrust angle is positive when the axle is pointed toward the passenger side of the vehicle, and negative when the axle is pointed toward the driver's side of the vehicle. RP 642 specifies a lateral offset target value of 0 inches, and manufacturers generally recommend a tolerance range of positive 1/8 to negative 1/8 of an inch. RP 642 also specifies a target value of 0 degrees for the axle thrust angle, and a tolerance range of positive 0.14 to negative 0.14 degrees, or 1/2 inch of lateral deviation over a 200-inch measurement distance. Furthermore, manufacturers generally recommend that the difference between axle thrust angles should be less than 0.08 degrees for a tandem drive configuration, to reduce drive axle steering. The next axle to consider is the steer axle of the vehicle. The wheel geometry of the steer axle is characterized by toe, caster, and camber angles. The toe angle refers to the inward or outward angle of the steer wheels measured from above the axle. The toe angle is positive when the steer wheels point inward at the front, and this condition contributes to the steering stability of the vehicle. A negative toe angle is when the steer wheels point outward at the front, which causes the vehicle to become less stable. It is for this reason that RP 642 only specifies positive toe angles, ranging from 0 to positive 0.16 degrees, with a target angle of 0.08 degrees. The caster angle refers to the angle of the kingpins, relative to the ground when measured from the side of the vehicle. The caster angle is primarily intended to improve the steering stability of the vehicle and has little impact on tire wear. When the kingpins are angled toward the rear of the vehicle, this condition is called positive caster. Turning the wheels either to the left or right with a positive caster angle requires the steering to lift the weight of the vehicle slightly. This lifting action makes the wheels naturally return to a straightforward orientation, which enhances steering stability. In addition to the lifting action, the caster angle also produces a change in the camber angle during cornering. The amount of camber change between the centered and cornering positions of the steer wheels can be used to calculate the caster angle of the kingpins. Given the goal of increasing vehicle stability, RP 642 only specifies positive caster angles of 3.5 degrees on the driver's side and 4 degrees on the passenger side. Manufacturers generally specify a tolerance range of 2 degrees to 7 degrees and may have different nominal angles depending on the axle. The camber angle refers to the inward or outward angle of the steer wheels measured from the front of the axle. A positive camber angle is when the steer wheels point outward at the top, and a negative camber angle is when the steer wheels point inward at the top. Manufacturers generally specify a tolerance range of less than plus or minus 1 degree and may have different nominal angles depending on the axle. Trailer axles are similar to drive axles in that they require careful adjustment of the thrust angle, and this adjustment can often double the life of the trailer tires. The thrust angle of the trailer axles also contribute heavily to the handling and fuel economy of the vehicle. The main difference is that trailers generally do not have lateral offset adjustment features. RP 642 also specifies the same target value of 0 degrees for the axle thrust angle and a tolerance range of positive 0.14 degrees to negative 0.14 degrees. The last key point of RP 642 is the recommendation for alignment as a preventative maintenance measure. A total vehicle alignment is recommended after a break-in period of 15 to 30,000 miles. The break-in period is when the vehicle experiences the majority of its dimensional changes from its original manufactured condition. RP 642 also recommends subsequent alignment checks every 100,000 miles. Even when following the recommendations of RP 642, there are circumstances like accidents or potholes that can produce misalignment between maintenance intervals. Since alignment discrepancies are generally too subtle to identify visually, the best indicator of an existing alignment discrepancy is uneven or irregular tire wear patterns. An excessive camber angle condition commonly results in a shoulder wear pattern that extends across the full tire tread. If the camber angle is excessively negative, the shoulder wear will be greatest on the inboard shoulder, and if the camber angle is excessively positive, the shoulder wear will be greatest on the outboard shoulder. However, shoulder wear that is symmetrical commonly indicates an excessive inflation condition, not an excessive camber condition. If the tire is underinflated, the greatest wear will be present on both shoulders. If the tire is overinflated, the greatest wear will be present in the center and the shoulders will remain unworn. An excessive toe angle condition commonly results in a symmetrical feather wear pattern of the steer tires. If the toe angle is excessively positive, the feather wear pattern will point toward the center of the vehicle. If the toe angle is excessively negative, the feather wear pattern will point away from the center of the vehicle. An excessive thrust angle condition commonly results in a biased feather wear pattern of the steer tires. If the drive axle thrust angles tend to steer the vehicle toward the driver's side, the feather patterns in both steer tires will point toward the passenger side. If the drive axle thrust angles tend to steer the vehicle toward the passenger side, the feather wear patterns in both steer tires will point toward the driver's side. Biased feather wear patterns may also occur from accident damage, such as when a truck drives down into a ditch. When the truck gets to the bottom of the ditch, the trailer will often hit one of the two frame rails and bend it downward. Even the slightest downward bend will cause the closest drive tire to carry more of the trailer load than the other three drive tires. The uneven load distribution can cause reduced traction and slipping in the three underloaded tires, while the overloaded tire has increased traction and tends to steer the vehicle to the opposite side. An out-of-balance wheel tends to produce cupping and flat spots as the wheel vibrates. The eccentric movement of the wheel increases and decreases the load on the tire in a consistent pattern, which causes the tread to experience localized wear at high load points. For more details on the Technology and Maintenance Council specifications for total vehicle alignment, Visit www.tmc.trucking.org to obtain a copy of their recommended practices, RP 642. For more details on performing an alignment, continue watching the Quick Align training series.